so if we can have everybody come on back in, we'll go ahead and get started with our second session. So as I mentioned, it's my absolute pleasure to introduce today's second session, and I want to thank the Welch Foundation for putting together this absolutely wonderful conference so far. I think we can all appreciate how multifunctional materials and hierarchical materials play a central role in our lives today, and I think what we'll also learn is that there's really a diverse array of ways that you can bring these materials together. You can perform research in order to advance these types of structures. And so today, we'll get a slice of that from our speakers, Joanna Eisenberg, Sharon Glotzer, as well as Peidong Yang. And so to introduce the topic, I think that we can all appreciate the inspiration we can take from nature with respect to this particular area of hierarchical and multifunctional materials. I put up just two examples of many, and I think we can all already identify exactly what these are from their macroscopic 3D structure. We can see that these are shells and spider silk, and we can ask the question of what makes these types of materials, among many others in nature, both mechanically robust and precisely functional. We know that the three-dimensional structure, of course, plays a role in this, but it goes beyond that, and we can take a closer look at the mesoscopic or even microscopic level, where we can see that there's a particular arrangement of multiple materials that play a role in creating these really unique sets of properties. You can go one step further and take another closer look and see that the combination at the interface of different materials, whether that be organic and inorganic materials for the case of shells, or amorphous and crystalline materials for the case of spider silk, play a particular role in this hierarchy that provides these unique properties. And what's really important to make a note of is the fact that it's not any one of these length scales that ultimately leads to these amazing properties and functionality, but it's really the synergy across those in multi-material types of structures that provides us with this. And so the question we ask is, how do we harness these types of materials and take advantage of them for our daily lives? And so one of the ways that we can think about this is bridging what the so-called abiotic-biotic gap. And so if we could create synthetic multi-materials, we could have a lot of different applications that could provide us with a way to interface our hard functional world, such as the electronics in our cell phones and on our computers, with the intrinsically soft and extensible biological world. And in doing so, we could create a number of amazing devices that allow us to enhance biomedical applications from stretchable electronics and soft actuators. But this question remains of how do we go about this? How do we create these hierarchical and multifunctional materials that rival or even go beyond those that we find in nature for inspiration? Now, fortunately, this is a multidisciplinary challenge, and we have a multidisciplinary set of researchers who are working on this. It goes, of course, from the foundation of chemistry as a central science, but beyond that, works together with a range of other disciplines from engineering and material science in areas that span from catalysis, advanced manufacturing, and characterization. And so with us today, of course, we're going to hear about different strategies to start to address this question about how do we create these really sophisticated multifunctional materials and hierarchical materials. Joanna Eisenberg will be up first from Harvard University on fabricating bio-inspired smart materials. We'll then have Sharon Glotzer from the University of Michigan talking about predicting materials assembly, followed by Peidong Yang from UC Berkeley talking about constructing nanowire devices. So what I'll do right now is provide just a brief overview of each of our spectacular speakers that we have lined up for today. So Joanna Eisenberg is the Amy Smith Barrelson Professor of Material Science and Professor of Chemistry and Chemical Biology at Harvard University. She's won a number of awards, and I highlight just a few here. She's in the National Academy of Sciences as well as the National Academy of Engineering, and the American Academy of Arts and Sciences. She's won the MRS Medal, the Kavli Innovations in Chemistry Leader Award from the ACS, the Ronald Breslow Award for the Achievement in Biomimetic Chemistry, and Harvard's Ledley Prize for the Most Valuable Contribution to Science. I share just a couple of really amazing pictures that have come out of her labs. Here's one on hydrogel actuated integrated responsive systems that we may see something about today, as well as liquid crystalline microstructures that was published back in 2018. Our next speaker, Sharon Glotzer, comes as the John W. Kahn Distinguished University Professor of Engineering and the Stuart W. Churchill Collegiate Professor of Chemical Engineering and Professor of Materials Science and Engineering at the University of Michigan, Ann Arbor. Again, really displaying the importance of interdisciplinarity in trying to tackle this grand challenge of hierarchical multifunctional materials. She will be talking about the assembly engineering for matter on demand. Sharon is also a National Academy of Sciences member, as well as a National Academy of Engineering and American Academy of Arts and Sciences member. She has won the MRS Medal, the Nanoscale Science and Engineering Forum Award, the Anisir Raman Prize for Computational Physics through APS, as well as the Fred Kavli Distinguished Lectureship in Materials Science through the MRS. Here are also a couple of really awe-inspiring images that have come out of her lab, clusters of polyhedra, spherical confinement, as well as solid-solid transitions in colloids. And then our final speaker for the second session today is going to be Peidong Yang. Peidong is the SK and Angelina Chan Distinguished Chair Professor of Energy and Professor of Chemistry at the University of California, Berkeley. He will be talking today about semiconductor nanowires, from nanolasers to photochemical diodes. He is also a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He's also won the MRS Medal and the Global Energy Prize, as well as the MacArthur Fellowship, the E.A. Lawrence Award, the Alan T. Waterman Award, the ACS Nanoscience Award, the ACS Backlund Medal, and the Julius Springer Prize for Applied Physics. Really inspiring images from his lab are these nanotree heterostructures, where you can again see the hierarchy that's kind of embedded within the materials that they are making. And so just as an overview for today's session, Joanna will be coming up in just a moment to tell us about multifunctional materials with self-regulation, followed by a discussion. Then Sharon will talk to us about assembly engineering of matter on demand. Then we'll take a break, followed by Peidong Yang, another discussion, and individual poster sessions with the discussions. When we do have questions, we ask that you also introduce yourself and where you're from, so that we can make sure we know where the questions are coming from. With that, I invite Joanna up to the stage to kick off the second session.